So the question says that a single crystal has a critical shear stress of 5.7 megapascal. So if we apply stress along the 001 direction of a unit cell, the final find the resolved shear stress for 111 plane at a 0 1 bar 1 direction slip system and determine whether the slip will occur. So when we apply loading perpendicular to a surface on some plane, for example here, we have a plane here. On some plane there will be a shear stress, and here we have a slip direction. And here we have a applied force, and here we have a slip normal to the plane. So the angle between the applied force and the slip direction is lambda. So the angle between the applied force and slip direction is lambda, and the angle between the slip normal to the plane and the applied force is P. So we can associate between the angle between these two, the angle of cos P and cos lambda, using this equation. So the resolved shear stress equals to the applied force, or sigma cos P, the angle between the slip normal to the plane and the applied force, times cos lambda, the angle between the applied force and the slip direction. But it is more useful to imagine this using an actual unit cell. So I will draw an actual unit cell here. Okay, this is our unit cell. And then we have a plane. We have a plane at 111. We have a plane. This is our plane here, 111. This is our plane, as mentioned in the question. 111 plane. So this is our plane. So this is X and Y and Z. So here we have the direction of stress at 0 0 1 direction. So this is the direction of applied stress. And then we have slip direction. Slip direction is at 0 1 bar 1 direction. So the direction of the slip direction at 0 1 bar 1, 0 1 bar 1 is at this direction. So this is slip direction. And then we need to find the slip normal to the plane. So our plane is here is a 111 plane. So the slip normal to the plane will be at 111 direction, 111 direction. So here, so this is our slip normal to the plane. And like what I have mentioned before, the angle between the direction of stress that we apply So the angle between 0, 0, 1 direction of applied stress and the slip normal to the plane at 1, 1, 1 direction is P, and the angle between the slip direction and the direction of stress is lambda. Okay, so now we have two arbitrary vector. Let's say that we have a and B. Let's say we have a and B. We have an A and we have a B direction. So there is, we have an angle between these two that we call as a theta. And we know that cos theta is the dot product of A times B divided by the length of the vector, the length of A times the length of B. Okay, so now we have a slip direction. We have a slip direction, and we have a slip plane, and we have a loading direction. So notice that at 1, 1, 1 direction, that normal to the 1, 1, 1 plane, this is only the case in a cubic system, and we know that the applied shear stress is 13.7 megapascal. So now we know that the applied shear stress equals to 13.7 megapascal, and then we can now determine the resolve shear stress using this equation. We have a 13.7, the applied shear stress, 13.7 megapascal times cos lambda times cos theta. So we can write it down like this, 13.7 megapascal. Okay, so now we need to find the dot product between 0, 0, 1 and 0, 1 bar 1. Zero, 0, 1 and 0, 1 bar 1. So we need to find the dot product between the slip direction and the direction of the applied stress. So 0 times 0 plus 0 times -1 plus 1 times 1, and now divided by, since we only have 1 here, so 1 square root times -1 square plus 1 square root, and now we need to find the dot product between the dot product between the 1, 1, 1, between this one, between 1, 1, 1 and 0, 0, 1 that direction. So we need to find the dot product between 1, 1, 1 and 0, 0, 1 direction. So 1 times 0, 1 times 0 plus 1 times 0 plus, and 1 times 1 divided by So we have a 1 square plus 1 square plus 1 square square root times, and since we only have a 1 here, so 1 square square root. And if we calculate the value of this, so we will end up with this value. We will get a 5.593 megapascal. So this is the shear stress for this system. This is the shear stress for this system. And if we look back at the equation here, since a single crystal has a critical shear stress of 5.7 megapascal, so since the resolved shear stress that we got here, since the resolved shear stress is lower than the value of 5.7 megapascal, this is the value of critical resolved shear stress. And since this value is lower than this value, so practically slip will not occur.